Previously on The Curiosity of a Child, we were pulled down into the depths of hell.
Rusty. The banshee agrees and goes back through the gates. Papa Legba, I asked that.
Anton, I only downloaded the free Kindle sample of the book, and the spell was cut short. The gate is still open.
Welcome to
The Curiosity of
A Child.
Episode 44.
Yeah.
Happy New Year to everybody. I hope you all had a wonderful Christmas and everything. Did you, Anton?
It was alright. Yeah, I did.
Okay, good. But should we get straight into the episode?
To the show.
This could possibly be our most dangerous episode yet, Anton.
Oh no.
So if you remember last time, we were dragged down into the pits of hell when our banshee summoning spell went wrong. And some of this was because we only had the free Amazon Kindle sample of the book. So I couldn't afford the full book. So maybe you could support us on Patreon, where we will be able to fund all the book buying and sound effects and hosting, and also your future education, Anton.
Yep, hopefully we can get better quality episodes, because at the moment I'm really stupid, as all listeners know. And also I think it would be nice to go on Patreon, get some exclusive rewards.
That's right, yeah. Which we'll try and put up.
Yep, no promises.
Yeah, no promises.
We'll do
we'll
our
have
best, though.
notes. We have a link on our website and on social media and in the show notes. But also I think another reason why our spell went wrong was because we were using the wrong elements. I mean, I don't think that actually wind, earth, fire and water are the real elements of how the world works, do you?
No, I think we're going to explore atoms, the real elements of this awesome world. I don't know. This episode, we're exploring the elements, the atoms that make everything you see, everything you touch, use and eat. They make up you.
That's right, yeah, they are absolutely everything around us. Now, do you know where all these elements come from? All these things that make us up and how they're formed?
Not exactly.
Okay, well, I'm no expert on this, but I've got a rough outline here. So we need to go right back to the very beginning of time. That's nanoseconds after the Big Bang.
So, just before Granny.
Just before Granny, exactly,
Yeah.
yes. Yeah. Now, the universe as we know it doesn't exist yet. Everything is just a mass of superheated particles that are speeding about and all smashing into each other. Then within half a second of these collisions, the first protons, neutrons and electrons were formed. Then in the next few minutes, the protons and the neutrons, they crashed together and they fused, creating hydrogen and helium nuclei, as well as small quantities of lithium and beryllium.
You're so good.
So these are the most basic atoms. So if you know you've got your nucleus in the middle, which has a neutron and a proton combined together, then electrons are on the outside.
Yep.
So these basic ones, they were just 1, 2, 3 or 4 pairs of neutrons and protons together, those elements. Now, after this mad rush of activity, things were calmer for nearly 400,000 years.
I actually forgot Granny was that old. Wow.
I know, it's shocking, isn't it?
I'm scared now for my life.
Well, we all are, as you'll find out.
Ooh.
But I wonder if time was passing really differently back then.
Yeah,
Because
so
time was kind of still forming as well itself.
see episode 40 for more in time.
That's right. And at this stage, the universe was more like a fog, and then you'd have light in all different directions. And in this kind of cloud, you'd have nuclei and you'd have electrons all whizzing around for another 1.6 million years until they cooled to a relatively mild 1,000 degrees Celsius.
Yep.
And then finally, the electrons started to join with the nuclei, and the first atoms as we know them were born. Now, the gravity of these new atoms caused them to cluster together into ever denser and denser clouds. This would generate lots of friction as they're all rubbing together, and they got so hot that they actually ignited and started nuclear fusion. So that's the stars being born. And then, so you'd have the gravity pulling in on the star, then you'd have all the heat energy pushing outwards, and they would find equilibrium, and that's a star. It's a balance between gravity pushing in, heat pushing out, and that's how they keep their shape.
That's cool.
And at the very centre of these stars, the temperature would reach 16 million degrees Celsius. And these extreme heats and pressures, the hydrogen and helium atoms, they vibrate hard enough to meld, and they form other elements like oxygen and carbon, so they actually merge together because there's so much kind of intensity there.
They're like crashing into each other, and eventually they just...
Yeah, and being like crushed together.
Yeah.
Think of a power up after you scored a goal or something. How hot that gets, it's horrible. And you're like, ugh! And that's how these poor little early atoms felt. But these are still classed as light atoms. So how do we get the heavier ones?
More crashing?
Pretty much, yeah. So when like really massive stars, far bigger than our sun, have burnt all their core away, converting it into iron, they begin to cool down. Then as they do so, the force of gravity overwhelms the heat that's pushing outwards, and they rapidly collapse, and the outer star will smash into the solid iron core. And this happens really, really quickly. So you get like a massive speeds, and there's all these particles in that, so in a big explosion.
So they sort of implode. Is that imploding, or is that different?
I guess it is an implosion because it's going inwards, yeah. And then there's so much energy in this explosion or implosion, so it goes supernova, and there's a shockwave that rips the star apart. As this happens, some of the atoms are fused together into heavier elements. And now all of these heavier elements, they start floating in space, and they're circling and reforming, and the gravity's all pulling them together again. And they become new stars, and more importantly for us, they become planets like Earth, full of all the wondrous and amazing elements that give us everything, including life itself. So we are all just one long-running chemistry experiment.
So I always thought the answer to life was 42, but it's actually elements.
Well, we don't know the question.
Oh,
because we know the answer. And the Earth was created as a giant computer to find the answer to 42.
Yeah. Okay.
Need the Hitchhiker's Guide to the Galaxy to get that reference. So I've got a chemical formula for you here containing a few elements. So can you just give our listeners a rough idea of what I've shown you?
Okay. So there's a lot of atoms. Hydrogen has 375 million, oxygen with 132 million, carbon with 85,700,000, nitrogen with 6,430,000, calcium with 1,500,000. That's quite a lot. And then there's a lot more different types of atoms after that. I'm not reading all of that.
Yeah, I think there's magnesium there, 400,000. So do you know what this is the chemical formula for?
42.
No. This is us. That's what humans are made of. But you have to times it by a few 100 trillion for each of those numbers.
Oh.
Now, shall we have a little experiment to just see how weird the elements are?
Okay.
And you can actually play along at home too. All you need is lots of the same thing. For example, some raisins or pennies or peanuts. Anton has now returned with some raisins. And he's going to put some on his plate. Probably need... That's enough, yeah.
Yum. Okay, so what do I do?
Okay, so each of these raisins, or whatever you've got, is going to represent one atom.
Okay.
Now you need to remember that all the atoms are protons, neutrons, and electrons just mushed together in bigger and bigger quantities.
Okay, 1 second. So are we making the human body here? So I got to get 3 trillion.
No, thankfully we're not doing the human body. We don't need that money. Okay, so if you take out one of the raisins from your pile, okay, now that's a hydrogen atom. So this is a gas. It's explosive. It's 2/3 of water, and it has 1 proton, 1 neutron, and 1 electron. And its boiling point is minus 250 degrees C. Now take a second raisin.
Okay.
And put it with the first raisin. Now imagine these being mashed together. This is helium, which is another gas. Now this is 2 protons, 2 neutrons, and 2 electrons, but it's not explosive. Take a third raisin.
Okay.
Now this is lithium. It's an alkali metal. And it's got a boiling point of 1,342 degrees C. And it's 3 protons, 3 neutrons, and 3 electrons. If you put that in water, it'll catch on fire.
I was about to put it in water.
And 7-Up actually used to contain lithium until 1948. Now, if you had a fourth raisin,
Yep.
how many neutrons, protons, and electrons do you have in that one?
4.
Yeah, 4 of each.
Yeah.
So what exactly are we doing when we add another raisin to represent the subatomic particles? All we're doing is adding more of the same stuff, aren't we?
Mm-hmm.
We're not doing anything else. Now, beryllium, if you take a fourth one, that is another alkaline earth metal, and it's transparent to X-rays, and it's used in nuclear warheads as it can block neutrons flying about. Now, if you've got 16 of them,
Yep.
don't worry if you can't count that high. Now, that's sulfur, and it's a non-metal. It stinks of rotten eggs, and it's bright yellow.
Uh-huh.
Now, if you go up to atomic number 29, that's copper, which is called a transition metal. It's reddish-brown, it's hard, and it's a great conductor of electricity. Add 4 more to that, and we have arsenic, atomic number 33. Once an important ingredient in green pigments, such as Scheele's green, it is also highly poisonous, and some people suspect Napoleon was killed by the green wallpaper whilst he was in exile.
Uh-huh.
Element 47, that's silver, a precious metal that was used to create mirrors as it's so reflective. But these reflections could be more permanent, as silver nitrate salt is light sensitive and enabled the earliest photography. 54 protons, neutrons, and electrons, you get xenon, a noble gas that glows bright when electrically excited, and is also used to power engines and satellites.
I like xenon.
79 is gold, melting point 1064 degrees, doesn't tarnish. Add 1 more proton, neutron, electron, and what do you get?
Mercury.
Yeah, mercury, melting point minus 39 degrees C, a silver-coloured liquid metal that's highly toxic. Then 1 more, 88, radium, radioactive and glows in the dark. Just from adding more of the same stuff together. So I hope that what you can see is that all the elements can be wildly different, and this difference is just coming from adding more of the same. It's like if you were to put your raisins in your mouth, and the first one tastes normal, put in 2 and it tastes of roast chicken, put in 3 at the same time, you've got vanilla ice cream that sizzles on the tongue. Eat 12 at once and you're poisoned, 65 and your head explodes. You're lucky that you were only eating raisins, and the combination of atoms that makes them up is really delicious. Some things contain much worse combinations of atoms than raisins. So how smelly was my Great London Stink recreation?
Disgusting. If you want to hear my live reaction, episode 30.
Yeah, it's a good one. Well, in these, you got some combinations of atoms in that molecules, which are propythonium and methanethyl, and they're much worse. And these 2 combinations of atoms are so bad that they can cause unconsciousness, spontaneous vomiting, and even death.
The Euphorbia resinifera plant contains a chemical with a Scoville heat unit value of 16 to 160 billion. The hottest chili is only about 2 million Scovilles. That's spicy enough to kill.
That's crazy. That's really hot. There's another chemical that's 230,000 times sweeter than sugar as well.
I want to try that.
I think that'd probably kill you as well.
Oh, I don't want to try that.
But as crazy and exotic as they sound, all these things are simply made of the elements the same as everything else. So these basic elements, these atoms, they're both really simple yet magically complex at the same time. But if they're so random in their behaviours, how can we ever hope to understand and harness their potential? Well, first we need to find them, don't we? And some are really rare. So there's a single flake of protactinium, which weighs 125 grams in the entire world. That's all there is of it. So how do you find something far smaller than the eye can observe, something too small to even reflect waves of light?
Well, probably the first people to understand the world is made of incredibly small building blocks were the atomist philosophers of ancient Greece. Born around 460 BCE, Greek philosopher Democritus was Democritus was a central figure in the development of atomism, the theory everything is made of tiny particles called atoms.
I'll just interrupt here. So atom actually used to mean undividable, but we now know it is made of separate subatomic particles. Sorry, please resume.
Thank you. He believed that only 2 things exist, the atoms and the void. Void is space between atoms which allows matter to move. Without the void, nothing could move and nothing could change. To Democritus, atoms were indivisible. Nothing smaller could exist, and came in many different shapes, giving them different properties. Water was smooth and round, so able to roll and flow. Iron atoms were rough and jagged, clinging together to form a solid body. His atoms were also eternal. They were never created or destroyed, but the items they were made from could wear away and form new things.
So that's actually pretty close to how we understand atoms today. So it's amazing to think that he understood this purely by observing the world. So I guess from Democritus onwards, we just start to learn more about the atomic world?
No. A certain guy called Aristotle disagreed. He knew everything was made from wind, fire, water, and earth. We've already said this is wrong, and everyone seems to believe him.
Yeah, we know how much trouble that got us into last episode, don't we? Thank you, Aristotle. I just think he's heralded as such a great thinker, but in many ways his works held us back for such a long time. And it would actually take until 18th of July 1985 for a testable atomic hypothesis to be formulated by a certain Mr. Einstein.
Oh, I like him.
Yeah, good hair.
Mm-hmm.
Now, whilst working in the Swiss Patent Office, he came across a 1827 paper by a Scottish botanist named Robert Brown. And in it, Brown described the random movement of pollen grains floating on water, which is now called Brownian motion. And he couldn't explain it. So he actually thought the pollen might be alive in the water. And what Einstein proposed was that the pollen was being bombarded by water atoms. And then he created an equation to test this idea, writing,
"It is hoped that some inquirer may succeed shortly in solving the problem suggested here."
Brilliant accent. I actually thought I was in the room with the spirit of Einstein. And his theory was soon tested and proved to be correct. So we actually had evidence that atoms existed.
That's good.
We have actually since managed to photograph atoms using scanning tunneling microscopes, which can see distances smaller than the waves of visible light. And in 2013, IBM created a stop-motion animation using single atoms called A Boy and His Atom.
Yep.
And we'll have this in our show notes and on our Twitter at CurieChildPod, where you can watch the animation. You saw a bit of it the other day, didn't you?
I don't get how they made the atoms in that shape.
Yeah, I don't actually know how they move them. Maybe magnetism or something? I don't know. I've no idea.
Something like that.
Anyway, let's head back to ancient Greece. Now, despite atomism not catching on, there was an understanding that different metals existed, such as gold, silver, copper, tin, lead, mercury and iron. And I read in one of my books, but I can't find it now, that around one of the mines, there was actually silver bubbling out of the ground. So I guess there's geothermal activity there, which heated up, and due to the relatively low melting points, the silver or tin or whatever came to the surface. So the world was kind of seen as alive. Actually, Newton, when he was looking at the elements, he believed that they were alive because you get the veins of the ore, like in Minecraft, going down through the earth. They were almost like tree roots and things, aren't they? To the ancient peoples, each of these metals was understood to have different properties and values. So gold is seen as the most valuable, being bright like the sun and never tarnishing. Now, tin and copper, on the other hand, they could be combined to make bronze, a metal much harder than either alone, but also relatively easy to cast and work with. And then tin has a very low melting point of only 231.9 degrees Celsius. So we decided that we would recreate an old Roman casting technique where molten metal would be poured into moulds made with cuttlefish bones. So I actually, when you were ill the other day before Christmas, that's how long we've been working this episode, I went down the beach and I collected some cuttlefish. So I've got a little recording of that. And then we've also got a recording of us casting the metal.
And remember previous episodes we were talking about the divine phallus? We may have cast that. I think our video as well of us casting it will be on Patreon.
Yeah, I'm going to put that up on our Patreon.
So no one will see it.
You can see us in the wood burner actually making it. So let's play the recording. I'm down the beach looking for some cuttlefish, which the Romans would use when they're moulding tin items. They'd actually carve into the cuttlefish bone to make moulds. And you might be able to hear the roar of the sea behind me. It's quite a cool December morning. I haven't found any yet, and I'm down here by myself as Anton has unfortunately got his knee strapped up after a playground injury. Good hunting now, as I've gone up to the top of the beach where I should have gone before, where there's lots of seaweed and kelp and also all the cuttlefish bones here. So I've just got 2 full big sized ones which should be perfect for carving. Anton should be excited to see these, but he doesn't know about the experiment yet. Now we're actually using the fires of hell here from where the banshee took us.
Yeah.
So you can probably hear them roaring away because we are trying to fashion some tools in which to escape and return to you so we can actually record this episode properly. Mm-hmm. So I'm going to leave that in the fire so it's very low melting point. I'm just going to close the door for a bit.
Very hot. What's going to happen to our little pot?
Well, that's made out of stainless steel, which has a melting point of about 1,400 degrees.
Okay, so it shouldn't melt.
No, it shouldn't melt.
Wow, that is very, very hot.
Yeah,
I'm
that's
opening the
insane.
door there. My eyes are melting right now.
Oh. Right, can you...
Oh yeah, it's starting to melt.
Can you see how liquid it is?
Yep.
And the surface temperature kind of holds together like mercury looks. Right, should we have a go at pouring this then?
Yeah, I'm excited.
Right, let's put that back in. That's very, 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 very hot, so you can't touch it, okay?
No, I wasn't planning to.
Now, if we added some copper to that, what metal would we make?
We would, with tin and copper, we would make bronze.
Yes, exactly. So it only took, what, a minute or something to melt, is it? Right, now let's close the fire.
Whew.
And make sure everything's done. And let's just leave those, and we should take them out of the mould tomorrow and hopefully break off any of the like residue stuff left over. That was really hot, wasn't it? Doing that? So could you imagine how it must have felt doing this on an industrial scale 2,000 years ago, and maybe doing something with melting copper, which has got a melting point of over 1,000 degrees to make bronze? I mean, way hotter than we had there. For thousands of years, our experimentation with the elements have allowed us to grow and given us advantages, not only against nature, but also against our fellow man. So roughly 4,000 years ago, we alloyed copper with tin to create bronze, so hard and malleable and perfect for tools and weapons. It was a huge advantage over stone or wood. 1,000 years later, we had replaced bronze with iron, forging stronger blades with which to conquer, ploughs with which to till, and tools to harvest and build and create. So important were these materials that we actually named eras after them, didn't we? The Bronze and the Iron Ages. Empires were built on bronze and iron and gold.
And as we said at the beginning of the episode, the elements are the building blocks of the universe, which have accompanied us on and been such a big part in our early technological evolution, so naturally also found their way into our culture.
That's right, not always in material form, but sometimes in language itself. Pliny the Elder wrote about gold.
It is the only metal that loses nothing by contact with fire. Perfect.
So how is something marked as the best?
It is gold standard.
Yeah, it's called the gold standard, isn't it? Or something. Like, is the gold, it's the top, it's the best. Or you think of the medal tables. Mm-hmm. Or if you've got a fancy credit card or bank account, then that would be platinum. So where does this idea of value come from? It could be from 2 scientists who in the early 1800s purified platinum from platina and sold it at 6,000% profit. Or if you want to make a product that's seen as quality or clean, what element would be good for that?
Silver?
Yeah. And it also has, you can use silver oxide, can't you, on keyboards to keep them clean and door handles and things in hospitals. Mm-hmm. Now in the 50s, chromium was all the rage. It was the new hotness. And then came titanium. So if you add that to your product name, it gives it a modern, sophisticated feel, doesn't it?
All new titanium toilet cleaner.
Yeah. It's not always positive though. So radium was once the new darling, but not for long when its dangers became apparent. It's the unique properties when protons, neutrons and electrons combine into all the materials in the universe that give us our love of them and also drive us crazy. As Pliny said,
The first person to put gold on his fingers committed the worst crime against human life.
that's a pretty big statement, isn't it? Mm-hmm. Our obsession with wealth and gold and materialism. Ever since, the fate of humanity has been linked to that of the elements. We knew of a handful in ancient times, but the discoveries would start to dry up during the Middle Ages. Then in the 1700s, incidentally, when we started to get really good glass, things really began to pick up pace. Modern practices, scientific theory and reasoning all led to a flurry of new discoveries and inquiry. China, for so long the dominant scientific and technological force, began to give up some of its lead to Europe in the late early modern period. And the use of silicon dioxide to create glass was one factor, as it was adopted across Europe, but not in China, where there was a preference for porcelain. So if you picture a science lab, what do you see?
Glass, beakers and flasks, test tubes.
Exactly, yes. There's lots of glass there, isn't there? Mm-hmm. And then what's amazing about glass is it's very chemically inert. So you can put all sorts of things in there and it won't react. And it's also impermeable, so it holds liquids in. So it was a massive enabler of chemistry. So without glass, modern chemistry wouldn't have been possible. Pioneers such as Carl Wilhelm Scheele, Joseph Priestley, and Bernard Cortese now had the apparatus and basic understanding to go in search of and separate different compounds and elements. So you think most of them, when you don't find most elements in their pure states, they're always going to be mixed in with other material. Mm-hmm. But to you and me, may still go unnoticed, even though they allow the modern world. But then you selected a few elements you liked, didn't you?
Mm-hmm. So my first one, xenon. Let me get my special book of knowledge.
Okay, and I'm going to look at my periodic table. So that's atomic weight 54, xenon.
So I like this because it looks really cool, and I think it's a gas.
Yeah, it's one of the Nobel gases.
Mm-hmm. I just like the look of it. Let me read a little bit about it to you.
Okay.
Xenon is so rare that there's only one atom of this gaseous element for every 10 million other atoms in the air.
Wow.
I'm looking at the one next to it now, and I wish I picked krypton because that looks cool too.
Well, krypton, that's another Nobel gas. Mm-hmm. Now, what's amazing about these is when you run or electrically stimulate them, they all glow. And xenon will be used in car headlights to make them brighter. And a 2019 RAC study showed that 60% of drivers, so they get dazzled by oncoming vehicle lights, and 70% get dazzled by them in the rear view mirror. And 91% of people said that car lights are too bright now, thanks to xenon.
Let's start a Kickstarter to make new not so bright lights for every car.
Well, yeah, I don't think that's going to be a hard sell, that one. Mm-hmm. All the Nobel gases, they're actually really chemically inert. They don't react with many things. They're very stable. Okay, so I think you've got another one. You've got bismuth now, haven't you?
Yeah, bismuth is my favourite looking one.
Chemical element number 83.
We'll link some pictures to bismuth, I think, because it looks really cool. Nice colour.
Just the one with all the square crystals?
Yep. I'm not sure if this is 100% correct, but from memory, bismuth was our first element that was discovered by a scientist. It's radioactive, but still it's weirdly relatively stable.
Oh,
it has been for the last few million years.
Actually, yeah, the half-life's very, very low, and that was for a long time it wasn't thought to be radioactive. Did you know that you can actually dissolve it in nitric acid, and you would create a white-coloured cosmetic that was similar to lead? But it wasn't as dangerous as lead, that would pock your skin. Yeah. But with the bismuth-based one, during a day out in the cities, all the sulphur in the air from the coal burning, it would turn your face a kind of browny colour, or rather the cosmetic a browny colour. But it's still used today in some cosmetics to give a pearlescence.
Nice.
Should we go on to the next one?
Yep. Tantalum.
And this is element number 73.
I think what drew me to tantalum was, well, once again, it looks really cool, but it's got some uses that I wouldn't expect, like artificial joints. So if you have a hip replacement thing, yeah, I know. Tantalum has the third highest melting point of any element, 3,700 degrees Celsius, making it perfect for use in nuclear reactors.
Yeah, nice. Do you know how it got its name? Oh, it's named after a Greek king called Tantalus, and he was punished for stealing from the guards. And what they did, they put him in a pool of water that he was unable to drink from. And it's because, again, it's pretty inert, it doesn't react very much. So I think that's why it's going to be good for medical uses, because you can put it in the body and it's not going to do anything bad. Unfortunately, it's also got a bit of a downside to its history, because it's really important in modern electronics. So you can make very small components with it, so mobile phones and stuff aren't possible without tantalum. It's also quite rare, so it's led to international tensions. And during the Civil War in the Democratic Republic of Congo, it's actually being used to fund both sides fighting against each other. So again, it's showing that, like Pliny said about gold, isn't it? It's our obsession with these materials.
Then next one is vanadium or vanadium.
It's element number 23.
I like the look of this one. I like the red crystals. I also got drawn to it because it's found in a mushroom as well.
Okay.
And some of the uses of it is to make tools, which have been alloyed with steel and vanadium.
Yeah, that actually makes it more resistant to vibrations and shocks. You only need 1% of it added.
And also I quite liked the Damascus steel knives from Babylonian times, is it?
I'm trying to think when they go back to, yeah. I always remember Damascus steel from
the
like the
capital.
Saracens, which you can't call them that anymore, though, can you?
The capital city of Syria,
Yes.
Damascus. So
Yeah, and the
Very
Crusades. Yeah, it's important to keep us healthy as well. We need really small amounts of it in our body. And like you said, you get it from mushrooms and shellfish, spinach and black pepper.
ooh,
Which is episode 36, if you want to know the history of pepper.
we've linked a lot of episodes.
We have. And right, let's do one more element that you've chosen, which is zinc, your last one, which is an element number 30. So it's 30 protons, electrons, and neutrons.
I like zinc because at school I have been doing some experiments with it. We've done some experiments with our Mel Science kits, which are really good as well.
Yeah.
And the ore of it looks a lot cooler than I was expecting.
Oh, wow, that's so shiny.
It
And they
is.
top the kind of cubes as well, pinky black cubes. That's very cool. Yeah, so zinc, you can alloy it with tin. And I actually tried to do that when we were doing our melting of our tin, but it was a little bit scary without the proper equipment, because you've got to get much hotter for zinc. It's up to 600 degrees, I think. And you can also mix it with copper, create brass.
I think that we've done that in one of our Mel Science things.
You did, didn't
It
you?
was called turning silver into gold, but it was the mixing the zinc and the copper.
Yeah, so you did that chemically rather than with heat.
Yeah.
I forgot about that, yeah. And yeah, so brass was actually known as a metal before zinc, because you often get it occurring in the same ore, in the same place. So when they dug it up, it was already sort of pre-mixed. Anyway, so that's a few elements that you like, isn't it?
I like elements, actually, now I think about it.
They're really interesting. I mean, I've been fascinated during all the research here. When you really start to think about them, it's like, mind blown. But there's something missing from our story. So we've looked at all these incredible elements and their properties, but it's all a bit random, isn't it?
Yeah. I think that it's been so chaotic because we don't have a table for them. I think we might call it the periodic table of elements.
But could you put them into a table? Because they just, to me, we're picking them up and one's exploding in water, one's kind of a gas, another one's a metal.
Can we sort them
melts.
by the number of protons and stuff they have?
Well, let's see if anybody's managed to do this, shall we?
Yep.
So why is one thing a metal, another a gas? Why does one glow and another conduct electricity? Is there no order to this chaos? Is there no guide for scientists? Enter.
Dmitry Mendeleev, Russian chemist and highly bearded man.
Yeah, he's got lovely beards. There he is there at his desk. We have a picture in the show notes. Now, he was born in 1834 in a village in Siberia. And he was the youngest of 13 or maybe 17, I've read different accounts, children. And his father was a school principal and teacher, and his mother was from a well-known family of merchants. Actually founded the first printing house in Siberia. And there's his parents.
Hello.
Yeah, I know she looks quite moody, and he's got a funny tuft of hair on the top of his forehead.
He doesn't look quite so hairy.
No, he's got mutton chops though.
Yep.
Um,
We should just rate people and how hairy they are.
yes. The Neanderthal ranking.
Yep.
Okay, so yeah, his parents, they were certainly not at the top of society, but neither were they at its bottom. Now, when Dmitri was still a teenager, his father actually went blind, so he was forced to help financially support the family by teaching science. So I don't know what all his older brothers and sisters were doing.
No.
I don't know. Why does it come down to the youngest one? It's a familiar story. Right. But he was a really bright young man, and aged 15, his mother decided that he needed a better education. So they set out on foot to trek across Russia to search for a university for him to attend. Now, after nearly 3,000 kilometres and close to a year of travelling, they reached St. Petersburg. So if you look at the map there, mate, you can see how far he travelled.
Oh, yeah. It's a good job he didn't waste his education.
Yeah, it's a long way, isn't it?
Uh-huh.
But sadly, by the time they'd reached St. Petersburg, his mother, Maria, she was in poor health and she actually died.
Oh.
But not before she saw him attend St. Petersburg State University to study chemistry.
Oh, that's good.
So she didn't see all the success he'd gone on to have, but he would have made her proud. He was one of the greatest chemists of his day, and he was a natural and passionate communicator, rather like us. And he'd make...
We don't need the greatest chemist. We're just the greatest.
Oh, yeah.
Obviously.
And he'd go on to make one of the most important contributions to modern science. He would bring order to chaos. He'd make the elements make sense as far as that's possible. And he'd even predict the properties of unknown elements yet to be discovered. But how is this possible? What witchcraft could this be?
The periodic table.
Yeah.
There had been several attempts to organise the elements in the past. German chemist Johann Doberleiner categorised them by their properties, such as lithium, sodium and potassium reacting with water and being soft enough to cut with a knife. Prior to this, Antoine Lavoisier put them into groups of gases, metals, non-metals and earths. It was far from perfect, however. His gases contained light and heat, and the earth, chalk, etc.
Yeah, so not exactly the correct chemical arrangements there.
Or just
groupings.
Any element, correct element at all there.
Yeah.
The element of light.
Did you know that Lavoisier, he had a magnifying glass 2.6 metres wide? Well, really, it was what's called a burning glass. It was used to focus the sun's rays into a 2.7 centimetre point of really intense heat. So
That sounds like a pretty prime ant burner.
Yeah. You can think of it as a precursor to particle accelerators, really. And one of the ones he used was called the Great Burning Glass of Trudaine. And it could burn melt a copper penny in just 30 seconds on a hot day. You could also use it to burn gold and tin and even diamonds. And by doing that, he discovered carbon, which is element 6, and essential for life. I've got a picture here of one of the burning machines, and we have this in the show notes as well. So it's big, isn't it?
It is very big. It's a nice picture, actually.
Mm-hmm. Lavoisier, along with Joseph Priestley, who was also a theologian, talk about normative determinism, and Carl Scheele all discovered oxygen around the same time as well. So there's lots of activity going on in this period.
Mm-hmm.
So when heated, mercury combines with oxygen and it turns red, creating mercury oxide. Now, previously, the act of burning was thought to remove what was called phlogiston from the material being burnt. Now, phlogiston, which I think I'm mispronouncing, that was seen as a sort of essence of fires. It's a bit like the old elemental fire that you would have had with wind, water and air.
Mm-hmm.
However, when weighed, the mercury oxide was heavier than the original mercury, so that meant that something from the air, a gas, had to have been combined to increase its mass. Of course, to be able to do that, you need to have loads and loads of mercury. You can't just do it on one atom, because we had no way of measuring things that small. Now, further experiments were made, including reversing the process, which released the oxygen, which Priestley wrote about as, "My reader will not wonder that, after having ascertained the superior goodness of the deflogicated air by mice living in it, I should have the curiosity to taste it myself. I have gratified that curiosity by breathing it. The feeling of it to my lungs was not sensibly different from that of common air. I fancied that my breast felt peculiarly light and easy for some time afterwards. Who can tell but that, in time, this pure air may become a fashionable article in luxury? Hitherto only 2 mice and myself have had the privilege of breathing it." And he was right. It did become a fashionable article of luxury, with people using oxygen tents today. Also amazing, he was like the first person to experience pure oxygen.
And then the 2 mice.
Lavoisier, he would go on to discover what water made of. So what 2 elements is that?
Hydrogen and oxygen.
Yeah, and it also ascertained that the air that we breathe is mostly nitrogen and oxygen. So amazing how through all the apparatus that have been developed, they're able to combine and separate different molecules and compounds and then isolate these different chemicals, or atoms and elements rather. Well, sorry, we were talking about the periodic table, weren't we?
Yep. In 1863, Englishman John Newlands arranged the 63 known elements in ascending order by atomic weight and discovered they almost followed a cyclic pattern. He put them into rows of 7 elements. So 1, 2, 3, 4, 5, 6, 7, and then 8, 9, 10, 11, 12, 13, 14, etc. So the second row would start at the 8th element and the 3rd, 15th, like I said, etc. He called these periods.
So this is like journals or magazines being called periodicals, because they're published at regular intervals. So there's a regular repeating pattern, it seems.
The columns he called families, and they contain similarly behaving elements. There was a problem with Newland's table, though. It was wrong. It didn't work.
What? Okay.
When some elements such as cobalt and nickel didn't fit his table, he put them in them both in the same box and called them the same element. This is where the genius of Mendeleev comes in. He made a deck of cards containing the elements, allowing him to play with their position and grouping. The cards made it easy to reposition and experiment. I like cards.
You do like cards?
I do like cards.
And that's also shown the importance of play in experimentation.
And on 17th of February 1896, after 3 days and nights without sleep, he collapsed on the floor, exhausted, surrounded by his cards.
Dead?
No!
Phew.
He had a vivid dream of his cards dancing before his eyes, a dance of the elements and the organisation of matter itself. As they danced, they fell into place, and they did follow a cycle, but not the forced one of John Newlands.
Amazing. Quite poetic somehow as well. Did you know he was also a consultant for the government, where one of his tasks was improving agricultural productivity and cheese making. And we all know that cheese gives you odd dreams.
The 63 elements we had discovered weren't the complete set. There were holes in the table, in the cycle. We were missing 32, germanium, 61, promethium, 72, hafnium. By leaving spaces for these unknown elements, order could be given to those we didn't know.
Yes, it might seem obvious to us now that there were holes in the table, but it can be hard to appreciate just the genius of this idea, because it seems so simple, but we don't know what we don't know, do we?
Exactly, and why would there be holes in the table?
Yeah. These scientists, they were trying to categorize the most diverse range of materials that make up everything, materials that are too small for us to see, materials that change properties with temperature, materials that mix and combine. I mean, amazing to be able to find that pattern.
And with Mendeleev's table, chemists were able to predict the properties of the missing elements based on their column and position. Suddenly, the atomic world started to make sense.
But now the question was, why do they follow this cycle? I'm going to try and simplify this for you as it's quite complex, okay?
You mean you don't understand? It's easy.
Okay,
I'm
on
the
to the
genius.
basics. And this comes down to, well, basically the number of electrons they have. So if you remember back to the beginning, the atomic number increases with the number of protons, neutrons, and electrons. The electrons orbit the nucleus, don't they?
Mm-hmm.
So as the number of electrons increases, so do like the layers in which they orbit, or what's called shells. So if you've got a periodic table which shows you the electron orbits, this way it gets scientific, you'll see that within each column, you will typically have the same number of electrons. So if you look at the noble gases, so that's going to be the far right-hand column of your table.
Uh-huh.
And you'll see that the last, or the outer shell on all of them contains 8 electrons, doesn't it?
Uh-huh.
If you go one column to the left, where you've got fluorine, chlorine, bromine, iodine, etc., the outer shell contains 7.
Uh-huh.
Okay?
Mm-hmm.
Then if you go to the first column, you've got, potassium and sodium and things in there, I think it is, isn't it?
Yep.
And then they have only 1 electron in their outer shell. Now, it's actually the number of electrons that they have which gives a lot of the properties of the element itself. So the noble gases, all of those, when they react with the electricity, like xenon, they illuminate, don't they? Mm-hmm. And then with the potassium and sodium, put those in water and they catch on fire. So that's a really key factor for how they behave. And that's what the period is, that's what that cycle is, and that repeating. You also get the electrons, how they orbit around the nucleus. It forms different shapes. And these are shared by groups of elements as well. And that's where we get like our metals and non-metals and our noble gases, etc. from. It's from the shapes that the orbits make. And then finally, some atoms, they actually like to trade or share electrons. And this is what's called covalent bonds. And there's a couple of different ways this can happen. So what most atoms will want to do is try and get 8 electrons in their outer shell. This is called the octet rule. And this is when they're at their most stable and least reactive, which is why the noble gases don't react with many things. So if you take your last column of noble gases with 8 on, now each side of that is going to be elements with 7 to the left of it and 1 to the right of it, yeah? Because remember the table's looping for each row. Uh-huh. Which means
the
that...
cycle again.
Exactly.
Yeah.
It's the cycle, yeah. So when elements from these 2 columns come into contact with each other, they are going to try and share electrons in their shell. As an example, you've got element 11 is sodium, and then that's got, 1 electron in its outer shell, doesn't it? Uh-huh. Then element 17 is chlorine, and that's got 7. So what happens when you combine chlorine and sodium together?
You get an 8.
Yeah, so what's going to happen is the 1 from sodium, it's going to hop over into the chlorine. What is sodium chloride?
Salt.
Salt, exactly, yeah. Common table salt. Another example is water, so what's that made of?
Oxygen and hydrogen.
Yeah, so oxygen has 6 electrons in its outer shell. Then hydrogen only has 1, but it's H2O, isn't it? So it's 2 hydrogen, 1 oxygen. So what's that add up to?
8.
8, exactly. So that's why they form these bonds and combine together. And then what you'll find is because of how elements, atoms want to combine together with other ones to become stable, you don't often find them alone by themselves in nature. They're always going to be in these different combinations of these molecules, which is something I'd like to look at in a later episode to actually discuss more. It's about 7 million different compounds that we know about, and there's actually a new one recently discovered on a meteorite that hit the Earth. So there's a lot more to it than what I've explained here, but this basic principle helps you understand why many elements behave the way they do, and why they react, and why they form molecules. When put into the periodic table, we can suddenly see why lithium, sodium and potassium all react with water, and why xenon, neon and argon glow when electrically stimulated, or why some elements are not as conductive as others. It gives order to the invisible. The periodic table shouldn't be remembered as a chart of random numbers and letters on the classroom wall. It's so much more than that. By understanding a few simple rules, you unlock the building blocks of the universe. There is a beauty in its structure and in the elements that it charts. They give rise to the magnificence of nature, of the stars that take our breath away, of the air we breathe, the food we eat, of life itself. Every taste, feeling, sensation and emotion we feel ultimately boils down to the chemistry of the elements. Simultaneously complex and incredibly simple, visible and invisible, solid yet mostly empty space, they are a paradox of our reality. For thousands of years we have strived to understand the building blocks of the world, but their story is so much longer. It stretches back to the beginning of time itself, and it will continue until the very end. We are made of the remnants of exploded stars, and long after our death, when no trace of humanity exists, the atoms that form our bodies and allow us to hear and understand the words that I'm saying now, they could be part of a new star or even a new alien life form. I think this is reason enough to want to understand, to want to know our place in the universe. Many of the scientific pioneers follow dead-end paths, such as trying to convert lead into gold, or experimented purely out of curiosity or discovery. And the understanding or discovery of these new elements happened by accident. And this can be science at its best: play, discovery and curiosity, not for a fixed outcome with budgets and deadlines and performance reports, but just for something new, for something undiscovered. And should we treat it more like art, as something creative, as ultimately a medium in which we find our place and our meaning?
Very good.
Maybe I got a bit passionate there.
I mean, why not? It's everything that we just talked about.
Exactly. Because you get people saying, oh, why do we spend millions growing plants in space when people on Earth are hungry? But that's the wrong question, I think. It should be, why do we spend millions on a single football player or a painting, or billions on entertainment or buying Twitter? Really? Because through all of this exploration and scientific knowledge, we can then progress ourselves as a species. Actually, one thing that I was reading about, petrol and cars used to have lead. They said that when there was lots more lead in the air, because of that, people's average IQ dropped by 12 points. So that's why you're cleverer than I am. But
And I was stupid as well at the beginning of the episode.
So just I was imagining a point where in the future, where if we don't understand these elements or these chemicals or what we're doing, could it be where we start putting so much of X, Y or Z into the atmosphere that we reach a point where we're too stupid to fix it? And yeah, that's our episode on the elements, mate.
It's good. All I can say, it was good.
One last push, go on.
One last push. It was really good.
Oh, wow, thank you. Yeah, so I'd like to do a little bit more on maybe chemical compounds and things, because this was looking at the structure of the atom mostly, and a little bit about the discoveries.
Maybe a mini-series on individual atoms as well. Maybe that could be on a Patreon.
Oh yeah, that's a good idea.
Patreon, we're actually doing stuff.
I hope we've done okay. It's our first time we recorded for 2 months,
Yeah.
so a bit rusty.
I still got a bit of a blocked nose. That's why we couldn't record. Because before, every 5 minutes I was just sniffing, so...
Yeah.
And also we were locked in the pits of hell.
Oh, we were locked in the pits of hell, and we have escaped. So remember, you could back us on Patreon, where I'll be able to cover cost of books and then buy Anton a great education.
Mm-hmm. Please do.
Speaking of which, you can follow us on Twitter at
CurryChildPod.
That's right, Instagram.
At CurryChildPod.
Yeah, you could also find us on Facebook if you look there. Yeah, so find us on social media, come say hi, visit our website, which is the...
CuriosityOfAChild.com.
That's right.
Buy merch. Shops.thecuriosityofAChild.com.
Oh yeah, check out Anton's 12 Days of Christmas YouTube videos where he does little builds, Christmas themed, which are really good.
That is The Curiosity of Gaming on YouTube.
That's right, yeah. So thank you very much for listening. I hope you found this interesting, and I hope I didn't make too many mistakes with the science. Thank you very much for listening, and we will be back soon with another episode when
Hopefully.
Well, what we're going to do next episode?
I don't know. Maybe we should ask our listeners.
Yeah, contact us. What do you want to learn about? We want to hear from all of you, and don't forget to review us at the same time. Wink, wink.
Maybe we'll do leave a review and ask and tell us what you want to hear next. Maybe we'll do a poll on Twitter as well, potentially, of a couple of different subjects. We'll see.
Yeah, that's a good idea. Anyway, thank you very much, and stay curious and look out for atoms.
I haven't seen any for a while, actually.
They're everywhere. Everywhere. Bye.
Bye. What would they have as hand protection, do you know?
They must have had some sort of leather gloves or
gloves
something
like
like these, I imagine. But the health and safety wouldn't have been at the level we... Well, health and safety.